Hello there and welcome to a brand new lesson. This is how Beyond Numbers, where we learn maths the easy way. In this lesson, we are looking at system of inequalities and linear programming. And by the end of this lesson, you should be able to graph a system of two or more linear inequalities and identify the feasible region. You should be able to find the vertices of a feasible region by solving pairs of boundary equations. You should be able to define an objective function and evaluate it at each vertex. You should be able to determine the maximum or minimum value of an objective function over a feasible region. And finally, you should be able to solve real-world linear programming problems using the corner point theorem. Now, over here, we have some vocabularies that you would hear me mention and then make use of even as we go through this lesson. I advise you pause at this moment and quickly take a glance, even though I would explain some along the way. I would also advise that you get your graph sheet, your notepad, your pen, and then your pencil so that you actually solve along as we proceed. So without much ado, let's quickly look into it. So let's start by looking at a general overview of what to expect. Now, when it comes to graphing a system, we simply want to find the feasible region. When we talk of a feasible region, if you would have noticed in the vocabulary, you said it is the overlapping shaded area satisfying all the inequalities in the system simultaneously. See, so that is our aim. That is what we want to look for. So if we take what we have over here, for instance, you realize that for this particular line, if I'm to shade it feasible region, this is what we have over here. So this is it. Then for this particular line as well, if I'm to shade its feasible region, this is what we have over here. Now, if you take note, you realize that there is an area where all these two feasible regions overlap. You see, that is our main focus in solving these types of systems. So our main focus is then going to be here, and I'm going to give that another color. That is this white one over here. That is the feasible region that is formed by all these overlapping feasible regions. Now, as time goes on, you realize that for most of these that we'll be solving for, our main focus is going to be on the first quadrant. So we would end up ignoring the second, third, and the fourth quadrant. So let me just clean these and then we focus here. So this is how it is going to look like. Now, if you're able to locate this feasible region, the most important thing now is, in order to optimize, that is either to minimize or maximize our objective function, then we take note of what we call the vertices. So with the vertices, what I mean is the corners of this polygon we have. So these are going to be my vertices. Now, this point here, which is the origin, is also a vertex, but it actually minimizes it, so our focus doesn't dwell on this coordinate, which is the origin. So we take note of these vertices. This particular one here becomes what? A 0, 4. So 0, 4. And then we have this one here, which is around, let's say 1.9, 1.9, then 2.5. Then we have this particular one here, which is also a 4, 0. So it is with these points that you now substitute into your function and then optimize it. This is a general overview. So now let's look at the steps that we'll need even as we solve some questions. So talking of the steps, we have just 5-step process. It builds upon what we've already done in our previous lessons. The first thing you need to do when you have the word problem, so the first thing you need to do is to define your variables. If they are x's and then y's, you define them and let us know what they represent. So you define both your dependent and then your independent variables. Then you now state the constraints. So on top of the constraints, they are actually the inequalities that restrict the feasible region. You see, so for instance, you have x is greater than or equal to 0 and y is greater than or equal to 0. Anytime you see this, it is telling you that we are only going to work in the first quadrant. You see, because in the first quadrant, that is where we have x coordinates being positive and then y coordinate as well being positive. Now when we talk of real world problems, if you are moving to the negative, then you're actually going to O. You see, you are moving to negative simply means you are going to O in terms of finances and all that. And when we talk of optimization, you actually want to make the best choice. You see, so we wouldn't make the best choice in the negative domain. So these linear programming graphs are mostly focused on the first quadrant. So you write all the constraints, including these we have over here. Sometimes you will not be told, but then you should always know that these are part of the constraints. Then you graph your feasible region. So we know how to graph our feasible region. We first of all identify our boundary, and then you take note either the boundary is part or it isn't. That determines the kind of line you draw. And then you then look at all the areas that overlap. So for this we have over here, we change the color to white, and it is the white that shows where everything overlaps. Then finally you find all the vertices. So just as I did over here, the vertices are just the corners of the polygon you have actually drawn. You see, then you evaluate your objective function. So as I said earlier on, the objective function is what you actually want to maximize or minimize. These are the 5 steps process. We now want to actually solve some questions, and as usual we would solve 5 questions in increasing order of difficulty, and I would advise that at each and every step you pause and try on your own before you come and look at the suggested solution. So our first question we have here, it says you have to find the feasible region for x is greater than 0, y is greater than 0, and then x plus y is less than 6. Then we have to list all the vertices. This is the very first question, and it's very simple and direct. So let's look at how we can solve it. And if you quite remember, I told you that for most of these problems we'll be solving, we'll focus on the first quadrant. So as you can see, I have just represented our first quadrant over here. I didn't add any of the quadrants. Now our first restraint here is that x should be greater than 0. So if x is to be greater than 0, then what it means is we have to focus on this side. That is to say, the whole of this side over here. This is x is greater than 0. Remember, if you want to be able to determine our regions that satisfy, we first of all look at the boundary region. So if we wanted to go strictly by that method, then we are going to say for x is greater than or equal to 0, we are first of all going to look at x is equal to 0. And you know the line x is equal to 0 is simply the y-axis. You see, so the y-axis can be called x is equal to 0. Then we now test all these regions. You see, either the ones on the right hand side and then those at the left hand side. You realize that only those at the right hand side that actually satisfy. So all this part, that is the first quadrant and the fourth quadrant. You see, now we go to why we have to focus only on the first quadrant. The next inequality says we have y is greater than or equal to 0. And for that as well, we have to look for the equation. So we have y is equal to 0. Y is equal to 0 is simply the x-axis. And if it is the x-axis, then it's going to be everything over here. Right? If it is the x-axis, it's only going to be this line. But if we want the region, then it is going to be everything above. You see, because we are saying it's greater than 0. So if I'm to shade that with another color, then it's going to be something like this. So you see, with all these regions, the two shadings are focused over here. You see, so with that, we then stick to the first quadrant that is working here. But we don't actually want our work to look this clumsy, you see, because it prevents us from looking at what is actually going on. So the rule of thumb is, anytime we have these conditions, then we just want to understand it mentally that we are working on the first quadrant and there's no need shading the x boundaries and then the y boundaries. No. Okay, so we have settled that. Then we now come to this inequality we have over here. So this particular inequality says x plus y is less than or equal to 6. Now to get its boundary, we say x plus y is equal to 6. Then at x equals 0, we have 0 plus y is equal to 6. And we have y is equal to what? 6. Hence, the coordinate that gives us is 0, 6. Then we also come to at y being equal to 0. We are doing this to look for both the x-intercept and the y-intercept. So at y equals 0, then we are going to get an x, then plus 0 is what is equal to 6. Making x the subject, we have our x being equal to 6. Hence, the coordinate this makes is what? 6, 0. So we come to our Cartesian plane and then identify these points. So our first point being what? 6, 0. That is it over here. And then our next point being what? 0, 6. So I'll bring that as well over here. Then what do? We draw our boundary line. Now our boundary line is going to be what? A straight or standard line, but not the dashed one. You see, so we draw our straight line through these points we have over here. You see, so I'm just going to make it long enough and extend this as well. So with this, we then want to identify the region that actually satisfies, because you take note that there are two regions. Now these are the two regions, as you have seen. I've shaded them heavily, but we want to look at the particular region that satisfies what we want to do. You see, so most of the times we said we take the origin to do that testing. We know the coordinate of the origin is what? 0, 0. So testing for 0, 0. Testing for 0, 0. We know the inequality was what? X plus y is less than or equal to what? 6. So for 0, 0, we have 0 plus 0. And is it less than or equal to 6? That is true. It is less than 6. So if this is the 0, 0, then it simply means our feasible region is going to be this side. See? So let me simply put my shading over there. And this is where our feasible region is. You see? Now our task was to list all the vertices. This is something we would be needing as we solve more complicated word problems. So talking of the vertices, we simply mean the corners. So this one here is a vertex, and then this particular point is also a vertex. And you remember I said the origin is also the vertex, but when it comes to optimization, we don't really use it. Okay, so our vertex, if I'm to write out our vertex, I'll simply say the feasible region is this triangle with vertex 0, 0, 6, 0, and then 0, 6. That is all for this question. Now before we look at our next question, there is one thing we need to know. We call it the corner point theorem. So talking of the corner point theorem, it says for a linear objective function over a bounded feasible region, we always get our maximum and minimum values at the corner. That is, for this particular one, this point over here, and then this point over here, and then this point over here. Those are the points we can get our maximum and minimum values. You see, now that is to tell you that there are so many points in here. So inside our feasible region, we have so many points. This is 1 1, this is 2 1, this is 3 1. You see, all these are points inside our feasible region. You see, they are feasible. That is, they make our objective functions work, and then they make it valid. But if you want the one that maximizes or minimizes it, our focus should always just be on the corners of the polygon. You see, so you don't necessarily have to check every time for all the points inside the feasible region. But if you want to optimize, that is to maximize or minimize, the focus is going to be on the vertex. We will apply that in our next question. For our second question we have here, it says we have to maximize p equals 3x plus 2y subject to, so we have x is greater than or equal to 0, we have y is greater than or equal to 0, and that is to tell us that we are working in the first quadrant. And then we have x plus y is less than or equal to 6, and then x is less than or equal to 4. Now this function we have here is what we call the objective function. That is what we want to either minimize or maximize. In this case, we want to maximize. And then these other ones are our constraints. So there are two ways to solve this: either the graphical or using your analytical method. Let me say using simultaneous equation. Since we are focusing on the graphical, I'll do that first, after which I take time to also do it with simultaneous equation, and then you take the one you prefer. That is, if you are not told to use the graph. So we say our objective function is p is equal to 3x plus 2y. And then our constraints are what? X is greater than or equal to 0. We know what that looks like. Then we have y is greater than or equal to 0. We also know what that looks like. Then we have x plus y is less than or equal to 6. And then x is less than or equal to 4. So let's focus on this. We have x plus y is less than or equal to 6. Our boundary line is what? X plus y is equal to 6. Now I think this was what we did in our previous question, and this is just its graph over here. So I'm just going to remove this, and then also remove the feasible region, and then these constraints we put over here. Okay, so there will be no need to actually solve it again. So with that said, we know what this is. That is, this gives us the first quadrant. X plus y is less than or equal to 6 is this line over here, and this is its feasible region. Okay, then the next one is what? X is less than or equal to 4. So to get x is less than or equal to 4, we have x is less than or equal to 4. We first of all look at x equals 4. So the line x equals 4 is this straight line over here. So I'm just going to represent it this way, this straight line. this is x equals 4. Okay, so I can as well extend it downwards. X equals 4. Then we look at the region that satisfies its, or that forms its feasible region, and we do that by testing for 0, 0. So testing for 0, 0, that is the origin. It says x is less than or equal to 4. All we need is our x value. So substituting for 0, we have 0 is less than or equal to 4, and that is what true. So that is to say this region, the region that is the region on the left hand side, is what satisfies this line. So that is all of this over here. But take note, if you look at our first line, it had its own feasible regions. Now its feasible region, that is this line, its feasible region was what we had over here, you see. And this time around we are taking this second one. This second one, we are also saying its feasible region is all the region on the left hand side. So that is to say everything within this range. But then if we look at the two, where do both intersect? You see, where do we realize that both are actually overlapping? You see, that is this region over here. So that is where our focus is going to be. So all I'm going to do is to what? Shade out that region clearly. And this here is going to be our feasible region, because it is the overlapping region of what? Our constraints. With that said, I'm not going to need all of this, so I have the liberty of cleaning them all. But if you are actually using a manual graph, there's no need cleaning. So with that gone, I'll just limit myself to the actual feasible region of all these constraints. Now, to be able to maximize or minimize, the corner point theorem says we should take note of the corners, you see, that is of our polygon. So we have, that is 2, and then we have 1 as well here. So we have all of these that represents our corner points. Now we take note of their coordinates. The coordinate of this particular corner point becomes what? 0, 6. So we have 0, 6 over here. And we have this coordinate as well, which is 4, 2. And then we have this as well, which is going to be a 4, 0. And then our origin, which is also a 0, 0. So with all these corner points or the vertex, you'd have to what? Test in the objective function. Or in other words, we want to evaluate the objective function at each point. So with that, let's form a table. So our table is going to have the vertex column and then the objective function. The first vertex we want to solve for is what? 0, 0. So for 0, 0, we know our objective function p is equal to 3x plus 2y. So substituting, we have what? 3 into bracket 0 plus 2 into bracket 0, and that simply gives us a 0. So at the vertex 0, 0, we have our objective function having a value of what? 0. Then we come to the next one, which was 4, 0. So doing the same substitution for 4, 0, it simply means that x is 4 and then y is what? 0. So we have 3 into bracket 4, then plus 2 into bracket 0. 3 times 4 gives us a 12, so we have 12 plus 0, and 12 plus 0 gives us a 12. So at 4, 0, the value of our objective function is what? A 12. Then we come to the next vertex, which was 4, 2. So for 4, 2 as well, we are going to do the same set of substitution, and this time around our x is 4, y is 2. So we have 3 into bracket 4, then plus 2 into bracket 2. We have a 12 plus 4, and 12 plus 4 gives us a 16. So at this particular vertex, our objective function gives us a value of 16. Then we come to 0, 6. So for 0, 6 as well, we do the same thing, and you'd get an answer of what? 12. So we then compare the values on this table. Remember, our question says we should maximize it. You see, and you see the step we needed to go through. You first of all work out your boundaries, identify your polygon whose vertex you'll be using to test for the objective function, and after the test it says we should maximize. So you take note of what the maximum value is. You see, if you look at it carefully, this is where we have our maximum value. It occurs at this vertex. So we conclude by saying, therefore, the maximum value of our objective function is 16. It occurs at the vectors 4, 2. I would want us to focus on the graph, so I would do a separate video where you could have actually used simultaneous equation to solve this. With that said, let's look at another question. We have 2 more questions, and for the last one, it is actually going to be a word problem so that we know how to apply this in what real world scenarios. Our third question we have here says we have to minimize. This time around it says minimize. So we have to minimize c equals x plus 3y subject to. So these are our constraints, and this is our objective function. So it is subject to x plus y is greater than 4, 2x plus y is greater than or equal to 6. You have x is greater than 0, and then y is greater than 0. So at this point, you should know what this means anytime you see them in your question. Okay, so with that, let's quickly look at what we are going to do. So our objective function, once again, is what? C is equal to x plus 3y, and our constraint. So for the first one, which is x plus y is greater than or equal to 4, we have x plus y, which is equal to 4. Then testing or looking for our boundary line, that is x plus y is equal to 4, we would say at x equals 0, we have 0 plus y is equal to 4. It simply implies that our y is equal to what? 4. And that gives us the coordinate 0, 4. Then at y is equal to 0, we have x plus 0 is equal to 4, which gives us an x is equal to 4. And that also gives us the coordinate 4, 0. So we can simply test for our origin so that we just know where we are going to put our feasible region. So testing, that is 0, 0. We have x plus y is equal to 4. And for 0, 0, it simply means x plus y is, we are using the inequality, so it's greater than or equal to 4. So we have 0 plus 0 greater than or equal to 4, and that is a for statement. So it simply means after identifying our boundary line, where we have the origin isn't the region that satisfies the feasible region. It is the other side. So let's quickly look at the second inequality. We have 2x plus y, which is greater than or equal to 6. our boundary line is 2x plus y is equal to 6. Now for y is equal to 0, we have 2x is equal to 6. Making our x the subject, we have x equals 3. And that simply means we are going to use the point 3, 0. Then at x is equal to 0, we have 2 into bracket 0 plus y, which is equal to 6. And that gives us a y which is equal to 6. And hence the point we'll be identifying is what? 0, 6. Now testing for our origin, that is to know which region is actually what satisfying. So we have 2 into bracket x plus y, which is greater than or equal to what? 6. And that is to say 2 into bracket 0 plus y. And y is also 0, so 0 is greater than or equal to 6. And that is 0 is greater than or equal to 6. Now for this as well, the region would be the opposite side because this statement is a false statement. So with this, let's quickly go to our graph and then see how it is going to look like. So this here is our Cartesian plane, and as we always know, our focus is just going to be on the first quadrant, so I just limited myself to that. With our first constraint, that is x plus y is greater than or equal to 4. The coordinates were 0, 4 and then 4, 0. So we just draw our straight line through these points. This here is my 0, 4. So 0, 4 and then through 4, 0. That is what we see over here. So I'm just going to extend this a little bit. Now from our testing, we realize that where we have the origin does not satisfy. So it simply means this region doesn't satisfy. And in other words, it simply means that this whole region we have over here, as I'll be illustrating very soon. So this whole region we have over here is rather the region that satisfies our inequality. All of this, you see. Okay, now we look at our next constraint, that is 2x plus y is greater than or equal to 6. And our points we came up with were what? 3, 0 and then 0, 6. So for 3, 0, this is our point over here. Then for 0, 6, that is it over here. So we draw this straight line through this as well. Now with this as well, we said its feasible region is also this side. So I'm coming to draw both feasible regions together so that we look at where they both intersect or they both overlap. So initially this was what I drew as the feasible region of this inequality. Now if I'm to add the second one to it, then this is how it is actually going to look like. That is this blue section over here, you see. So if you have to look at it critically, then where we have both intersecting is this whole region over here. So with that, I'm going to give it a new shade. I'm going to make it just a little deeper. So we have from this point all the way down, that is this region over here. So you see that there are still portions of the red one, you see. So I'll just remove all those from there, and this becomes the portion of interest. Now if you look at it critically, there are so many points in this region. There are so many points, but take note, the corner point theorem said if we want to maximize or minimize, then our focus should be on the vertices of the polygon. You see, that is the corner sides. And in this particular case, we have 1, 2, 3 corner sides. You see, so let's take note of the coordinates of these corner sides. So for this particular first one, it is what? Let's put our points over there, and then let's do same for this, and then this particular one as well. So these are corner sides, you see. And then what are their coordinates? We have 0, 6 right here, and then this particular one I think is 2, 2. And for this last one, we have a 0, a 4, 0. That is this one over here. So if you look at the question, it asks us to minimize. And looking at this point over here, you see the origin is not part. So this is to tell you that it is not always that the origin is the point that minimizes a function. You see. So let's draw our table and evaluate the objective function at these vertices, and then we look at the point that actually gives us the minimum value. So on our vertex, we have what? 0, 6, then 2, 2, and then the 4, 0. So we are evaluating the objective function on all these points. X plus 3y. So let's start with 0, 6. So for 0, 6, we have our c being equal to x is 0. So 0 plus 3 into bracket y, where y is what? 6. So we have our 0 plus 18. So that gives us an 18 at the objective function. Then we come to 2, 2. So for 2, 2, we have c being 2 plus 3 into bracket 2. That gives us a 2 plus 6. And 2 plus 6 gives us an 8. So at 2, 2, we have the value 8. Then we come to 4, 0. So at 4, 0, it simply implies we have our c being equal to 4 plus 3 into bracket 0, which then gives us what? A 4 plus 0, which is 4. So the value here is what? 4. So comparing all our values, at 0, 6 we have 18, at 2, 2 we have 8, and then at 4, 0 we have 4. It is obvious that this is the smallest value, you see. So we conclude by saying that therefore what our minimum value of c, that is the objective function, is what? 4. And then it occurs at what? 4, 0. Now if you want to test whether this is true or not, you can take any other points in here. So there are so many points inside this region. You can take any of them. You can even take 5, 0, 6, 0, 7, 0. We have the 6, 0, 6, 0, 7, all the points in here. And you realize that among all of them, the smallest is still going to be your 4, 0. So this is the theory behind linear programming. Now we'll solve our last question, which is going to be a word problem. You see how we can apply this in real life scenarios. So our next question, that is our last question, says a factory makes chairs and tables. Chairs need 2 hours labor and tables need 4 hours labor. Total labor is less than or equal to 40 hours. Chairs need a 1 meter squared material and then table need a 3 meter squared material. The total material should be less than or equal to 21 meter squared. Now, the profit per chair is 30 cedis, and that of table is 60 cedis. So what we want to do, we want to maximize profit. Let's maximize profit. We know how much it takes to construct these tables or manufacture these tables and chairs, and then we know how much each costs. So how do we actually maximize profit and not run at a loss? This is one practical application of linear programming. So looking at what we have, if we have to look at the variables we've been given, then it says our x is always going to be what? Chairs. And on the other hand, y is going to be what? The tables. So let's focus first of all on the total number of hours. It says chairs need 2 hours labor and then tables need 4. But the total hour is supposed to be less than or equal to 40. So if we combine the hours needed for chairs and then that needed for tables, it should all together be equal to or less than 40. It shouldn't be more than 40. Now that is to say 2 hours of labor for chairs. That is 2 for chairs, then plus 4 each for a table. So 4 of a table. You see, and that is not to be less than or equal to 40. This is one of our constraints. You see, so let me write that out so that we get to know that we are actually looking for the constraints. Then there's another constraint we can get over here. That is to say, in terms of the materials. So with respect to the materials, we need 1 meter squared for chair. So that is to say 1x. But we know for x, for 1, we don't actually write it. So we have our x, then plus the quantity of material needed for a table is 3. So 3y. And all together should be less than or equal to what? 21. You see? So these are our constraints. Now we should always know that for number of chairs, that is x, it should always be greater than or equal to 0. You see? And then the number of tables should also be greater than or equal to 0. So you see, this time around, we are now introducing this to indicate that whatever we do is supposed to be focused in the first quadrant, because you are not going to have a negative number of chairs. You see, we can't produce negative number of chairs or negative number of tables. So these are our constraints. Now we look at the objective function. What do we want to maximize or minimize? This time around, it is in terms of profit. So we want to maximize profit. And it says there is 30 cedis per chair and then 60 per table. So that is to say 30 per chair, that is x, and then 60 per table, and table was y. So we want to maximize this as our profit. This then becomes our objective function. So the most important thing when it comes to word problem is you actually being able to write out your inequalities you'll be using. If you're able to write it out, then everything follows in order. You see? So now that I've been able to write it out, I'm sure you can solve. So you can pause at this moment and then solve yourself and come back to do it together with us. So now that we have these, let's start with the constraints. Now we know how to go about it. First of all, we write them as equations, and then we look for their intercept, that is the x and the y-intercept. So for the very first one, we have 2x plus 4y. Let's change it to what? An equation. So we say equals 0. So at x equals 0, then we have 2 times 0. That gives us 0. So we have 4y is equal to what? 40. And our y is simply a 10. So that gives us the point 0, 10. Then at y is equal to 0 as well, we have 2x being equal to our 40. So our x is simply a 20. So that gives us the point 20, 0. So we are done with this first one. Then we now come and test. So testing with what? 0, 0. So at 0, 0, we have 2 times 0 plus 4 times 0, which is less than or equal to what? 40. So that is 0. This is 0 plus 0. So 0 plus 0 is less than or equal to 40. So it simply means the region where we have the origin satisfies. You see, then now we move to the second one. So we have x plus 3y equals 21. So with that, we have at x equals 0. So at x equals 0, we have our 3y being equal to a 21. Then our y will be equal to a 7. So that gives us the point 0, 7. Then at y is equal to 0 as well, we have x being equal to a 21. That is straightforward. So that gives us the point 21, 0. So we now test with 0, 0. So at 0, 0, we are going to get a 0 plus 3 into bracket 0, which is less than or equal to 21. That gives us a 0 which is less than or equal to 21. And that is also true. You see. So with all these, we can get our boundary line and then the feasible region, and we continue from there. So here on our graph, I'm using the scale 1 centimeter is to 2 units. And we have 5, 10, 15, 20, and then in that order. So with that, for the first constraint, which is 2x plus 4y is less than or equal to 40, we had our x-intercept being 0, 10. So 0, 10 is this point here, and then the y-intercept is 20, 0. So that is also this point over here. So we just draw a straight line to connect these 2 points. So just as I have done. So remember, when we tested, we had the origin. So this is the origin, right? We tested for the origin. We said the origin satisfies the feasibility region. So it means this side is what we are talking about. It satisfies. So let me just shade that quickly so that you see. So this is the region we are talking about, and it satisfies so well. Now we come to the next one, which is x plus 3y is what? Less than or equal to 21. So for that as well, so for its y-intercept, we have 0, 7. 0, 7 is going to, so we have 5, then 6, 7. That is going to be around here. Then we have the x-intercept being 21, 0. So we have 20 here, and then 21 is also going to be here. So let's join these two. So 0, 7 all the way to 21, 0. This point here. So with this, all I'm going to do is I'm going to extend it further. You see. So for that as well, how did we conclude on its feasibility region? We said when we tested for the origin, where we have the origin satisfies, you see. So if I'm to shade that portion as well, then we are going to have something like this, all of this being in the feasible region. But our most important area or feasible region we want is where they both intersect, you see. So if you want where they both intercept or overlap, that is going to be this region we have over here. So there is a vertex here, you see, and then we have the rest. Do you see that? So let me simply deepen that. So we have from here to here to the vertex down here, then it comes back here. So this is our polygon we are going to use. So now that we've been able to do this, the most important thing now is we identifying our vertex. So for the vertex or the vertices, we have 0, and then this is 7. That is for this point over here. So we have our 0, 7. Remember, it is this that will help us either maximize or minimize our objective function. So 0, 7, and this point here, if we have to trace, so it is at 1 and then 18. So we have 18, 1. And then for this, we have our 20, 0. And finally, this time around, we have our origin included. So 0, 0 as well. Those are the points of the coordinates. Those are the coordinates of the vertices of the polygon. Now, in order to maximize our objective function, we would have to test for the values of the objective functions of all of this. So that simply means we need a table where we put our vertex and then our objective function. Now we know the objective function was our profit is equal to 30x then plus 60y. So we will test for 0, 0, then we'll test for 20, 0. We will also test for 18, 1, and also test for 0, 7. So with that, we have our p being equal to a 30x plus 60y. So at x being 0 and then y being 0, that is at 0, 0. Then we have a 30 times 0, then plus 60 times 0. That simply gives us a 0. So at 0, 0, we have what? 0. It means if you produce 0 chairs and 0 tables, you are going to get no profit. That is what this simply means. For the second one, we have 20, 0. So for 20, 0, we have 30 into bracket 20 plus 60 into bracket 0. That is going to give us a 600. So this here simply means if you have to produce 20 chairs and no table at all, with all the materials, you're actually going to get 600, a profit of 600 cedis or whatever unit the currency is in. Then we have what? 18.1. For 18.1, it simply means you are producing 18 chairs and just one table with the same set of material limitations. So we have our 30 into bracket 18, then plus 60 into bracket, we have our just 1. So we have 30 times 18, which gives us a 540, then plus 60 times 1 gives us a 60. Adding this together, we have 600. So that is also going to give us a 600. Then we come to what? 0, 7. So for 0, 7, we have 30 into bracket 0, then plus 7, or 60 into bracket 7. When we evaluate this, we have 30 times 0, which gives us a 0, then 60 times 7, which give us 42, 420. So we have 420. Now if you have to observe what we have on our table, what is the implication? It simply means with the limitations we have, that is with the constraints we have been given, we can make maximum profit at two different points. First of all, we can choose to produce 20 chairs with no table at all. That would give us a profit of 600. Or we can produce 18 chairs and just one table, and that will also give us a profit of 600. That is what this means. So our conclusion is the maximum profit that can be made is what? 600, and is achieved at both 20-0 and 18-1. That is, you either make 20 chairs only or make 18 chairs with just one table. That ends our word problem and subsequently our problem solving for this particular video. I do hope this lesson was helpful and we're able to achieve or meet our objectives. As usual, I'll leave with some examples so that you try on your own. I would also advise that you pause at this particular moment and try these so that you test your understanding. So here you have 5 questions in the same order we have just solved, and I would advise you to try them. Let's have beyond numbers where we learn maths the easy way. If this lesson has been helpful, you can choose to subscribe if this is your first time and you so do wish. As usual, if there's any issue of concern, you can always let me know at the comment section. When I'm notified, I will address that for you. See you in our next lesson, and bye for now. Do stay safe.